Welcome back. The first approach we're going to talk about today is differentially private stochastic gradient descent. So now we already covered an approach which is very similar to this in the last lecture. That is the approach of Basili, Smith, and Thakurtha. But this was more the focus of this one was more getting the theory down, like making sure we could prove convergence, showing that what type of bounds we can get in terms of optimization and how much error. Whereas the focus of the paper that we're going to be discussing a bit more during today is going to be a result of Abadi, Chu, Goodfellow, McMahon, Mironov, Talwar, and Zhang, which is a paper called Deep Learning with Differential Privacy. And the purpose in this paper is to try to go beyond just the theory and make algorithms and run this algorithm so that it's actually effective in practice. And there's a few things that need to be done, a few tweaks that need to be made. In particular, one thing which is not too hard to deal with is the fact that the gradients or the loss function rather is not Lipschitz, and we need to somehow bound how sensitive it can be to a single point being changed. But the other thing which is more challenging is going to be dealing with the fact that when we use advanced composition, like we did a pretty cool analysis here. Remember, we used the Gaussian mechanism, we used subsampling, and we used also advanced composition. But even that leaves a little bit something to be desired in the sense that it's not really a tight analysis. There's some factors which will be lost. And in particular, one of the main contributions of Abadi et al. Is that they show that this can be done significantly better. You can do better analysis, and this will save you significant amounts in your privacy accounting. When I say significant amounts, I mean really constant factors. In theory, we often don't think about constant factors as being that important, but when it comes to the practice here, in terms of like how good the privacy is, these constant factors matter a lot. For example, if something is 1 differentially private versus 10 differentially private, this is quite a large difference. So therefore, despite these the guarantees here just sort of being for small factors, they actually make a big difference in privacy. And I'll show you some numbers so that you can see. I think you might have a good intuition by now about what a good privacy guarantee and a bad privacy guarantee is. So it'll tell you about how much we can really save in our privacy guarantees. So let's recall what the algorithm of BST is. So it looks something like the following. It's very simple. So we first select a random point, select xi, yi at random. So it's iterations of this procedure that I write here. But for each iteration, we select a point randomly, we compute the gradient at that point and multiplied by n, I guess, n grad of the loss function of the current loss vector, xi, yi, and we add on some Gaussian noise, which I'll just call capital G of t. And third step is we step in the negative direction. Of this gradient. Okay, so very simple. Choose a random point, compute the gradient, noise it, and use that to just select which direction to go. Very simple. Abadi et al. Is pretty simple as well, but there's a few minor differences. So let's try to walk through them. The first difference is that instead of just choosing a single point, we're going to select a lot of points, used in sort of the other sense of the word. And it's a lot, like a set of points. That's the word they use. And how do we select this lot? And why do we even use the word lot? Usually you might think, okay, don't we use the word mini batch here when we select a set? No, because this is going to be a slightly different sampling procedure than what you've seen before. So this lot consists of a set of points where each point is selected with probability L over n, where L is some parameter. So in particular, this will give us a lot with a expected size L in expectation. Yeah, where like I said, L is the parameter which we're going to choose. So we still draw several points. The next thing we do is that for each point in the lot, we compute the gradient. So let's just for now call this g sub I equals the gradient of the loss function theta of t xi yi for all I in the lot. Now the thing we have to do, remember the tricky part, or remember why we here when we did this, we assumed that the loss function was Lipschitz in order to be able to bound the magnitude of the gradient. However, we don't have any such bound this time because we have not made the assumption that our loss function is Lipschitz. So what we're going to have to do now is we're going to have to clip the gradients. So let me write it first and then I'll draw you a picture of what I mean. So clip gi to L2 ball of radius c and average them. So what do I mean by clip it to a L2 ball of radius c? Well, let me draw an illustration. So this is going to be our L2 ball. So this is the origin, and then we have this is of radius c. It's the dotted line. And the idea is the following. So what we want to do is we want to limit the sensitivity of our gradients. But like I said, they could be arbitrarily large. You could have a gradient that looks like this. This could be g sub I. Well, what we're going to do is we're going to actually clip this so that it has bounded sensitivity. So let me do it in the color here. We're going to sort of rescale it so that it lies within this L2 ball as follows, right there. So that's what we mean by clipping, essentially just rescaling it so that it fits within the L2 ball of radius c. On the other hand, if it's already smaller than the clipping radius c, then we just like leave it as is. Cool. So it might seem a little bit artificial or a bit silly, but this is an easy way to make sure that the sensitivity is bounded. And this is a very useful technique in general to make sure your sensitivity is bounded. Just clip the point so that, or clip whatever you're going to be noising so that it is indeed bounded by something and you can have the appropriate sensitivity bound. Okay, like I said, you average them. And I guess like the next step is, of course, you add appropriate noise. And step 5 is step in negative direction again. So, okay, let's let's sort of highlight the two differences. The one main difference is the fact that, the step 1 differs, selecting one point versus selecting a lot of points. And the second difference is the fact that we just take the gradient, and this one we have to actually clip it. So, right, let me just comment on this, the fact that, right, you see that we, just round it to the ball. Again, it seems kind of crude, but it typically works in practice. I'll comment one thing, that last time in the last lecture, when we were doing the accuracy of the BST method, we really required that the estimate of the gradient we got at each step was unbiased. That is, we selected a random point and compute its gradient. That would be an unbiased estimator, once you rescale by the factor n, of the gradient as a whole on the entire data set. However, when you do this clipping, that's not exactly the case. That's not going to be the case. The thing is, so we're not going to have the same sort of accuracy guarantees that we could provide before, but it turns out this is not really that big a deal, in the sense that we already lost those guarantees because of the fact that we're doing SGD in a non-convex setting, so we don't necessarily have the same convergence theorem. So you know, clipping and removing some data and making it potentially biased isn't that big a deal either. Right. So we'll see that this clipped SGD still seems to be reasonably effective in practice, despite lacking this convergence guarantee. Okay, so the other difference is the fact that, like I said, we don't select just one point. We select a lot of points. Oh, I guess I meant to discuss clipping down here, but maybe you already got the picture. The other thing is the fact that the sampling scheme, in particular, there's sort of a difference between these two different sampling schemes, and let's try to see what the difference is. In particular, you know, let me sort of write them right here. Select one random point and versus choose each point with probability L over N. So first thing I want to point out is you could see this maybe as generalizing this, but no, they're kind of incomparable. The reason being that even if you set L equals 1, then you would select each point to be in your set with probability 1 over N, but this isn't equivalent to selecting one random point. In expectation, you'll select one point, but it's possible, in fact, that you could select, you know, you could even with very low probability select N points. You could select, more likely you'll select 1 point or 2 points or 3 points or something. But yeah, this is just not the same sampling scheme. It's not a generalization of it. It's kind of incomparable. And there's a few different ways that you can choose to sample subsample points. There's this one here, which is called Poisson sampling, for kind of weird, unknown reasons to me. A lot of things have Poisson's name on it. But so this could just be Poisson sampling. Another thing is sampling without replacement. What does this mean? It means we sample, say, however many things we want, say L things. But once we select things, we can't pick them more than once. So this is pretty much the standard way you would pick. You would picture selecting a subset of a set. You just pick without replacement. And I guess most classically, this is kind of where the subsampling amplification results kick in. In particular, I think the one that we discussed last time in last lecture, that's exactly a sampling without replacement subsampling guarantee. So notice that in particular, this selecting one random point is sampling without replacement with just picking one point. Additionally, you can imagine sampling with replacement, which is kind of different in the sense that what you do is you pick, imagine you wanted to pick L items from a set. What you do is you pick one set item from the set uniformly at random, and then you keep picking from that original set again. You don't sort of remove the first thing you picked from potentially being selected a second time. So for example, you could just pick if you wanted to pick a set of size L, you could potentially just pick the first element L times in a row. So this allows some repetitions. I'll note that this is also a generalization of this one because when you're only selecting one point, there's no difference between without and with replacement. So why am I telling you about all of these different sampling schemes? Well, it turns out that they might seem similar to you, but from the viewpoint of privacy, there's important differences between these different approaches. In particular, we relied in the last lecture upon the amplification that subsampling gives. And this so therefore, depending on which method you use for subsampling, it'll result in somewhat different privacy guarantees. So in other words, you're going to really want to be careful about which way you sample and how you do your analysis, because these are really intrinsically linked. I'll notice that most analysis of DPSGD, in particular the one in Abadi et al., are based around Poisson sampling. This is not what people do in practice. What they do in practice is actually a little bit, it's actually kind of wrong, to be honest with you. It doesn't have the same type of privacy guarantee that Poisson sampling does. But essentially, it says the following. This is typically what's done in the non-private setting. So you randomly permute the data set, and you iterate over fixed size batches. You iterate over it, selecting fixed batch each time. Let's say B points each time. So if you just look at this from the perspective of one selection of B points, then this is equivalent to sampling without replacement, because you're just picking B random points, and if you randomly permute, they'll be indeed uniformly random. But however, this is not the same as sampling without replacement, because if you consider the first batch that you pick and the second batch that you pick, those will actually be correlated in terms of the randomness. So therefore, it doesn't immediately get the same privacy guarantees. I think there are some analyses of this, but the thing is, this is inherently different from all of these other ones, from each of the other ones, let's say, and people often in practice incorrectly use Poisson sampling in order to do the privacy analysis of this. So these are not the same, these are not equal. So just be a little bit careful about that. It's easy to just download TensorFlow and TensorFlow privacy and try to use it like that. But in fact, if you don't do it with the correct Poisson sampling, then it's not going to enjoy the actual privacy guarantees that are claimed. Okay, so that's subsampling. The last theoretical and most important theoretical contribution of this work is doing a tighter privacy analysis. So, let's before we continue, let's define some notation. Let's let the value Q be equal to L over N. So this is to recall the probability that each element of the data set, of the training set, is picked with during each iteration. So recall that in this case, how did we do the analysis in BST? The analysis in BST went roughly the following way. We used the Gaussian mechanism plus subsampling amplification, plus we used advanced composition. So that's good. Now, what type of guarantees would we have if we did this? Well, the privacy, what do I want to say? Really, let's focus mostly on the latter two parts. In particular, if you did it without, if you applied the Gaussian mechanism so that it would guarantee epsilon delta dp, then subsampling plus advanced composition will result in the overall thing being roughly the following privacy guarantee: O of q epsilon square root of t log 1 over delta, comma t delta differentially private, where recall t is the number of iterations, number of iterers. So right, this is the type of privacy guarantee we would get. Where does this all come from? Well, this factor q here, that comes from subsampling amplification that we used, and this root t and this t factor here, those come from essentially the advanced composition application. So that's pretty good. It's not bad, but in fact, the Abadi et al. Paper, the one we're looking at, they give a better way of analyzing this and are able to show something which is O of q epsilon square root t, comma t delta dp. So this might seem like a small improvement to you, or sorry, this is not t delta, it's just delta dp. So you can see the two places this really saves. It saves this log 1 over delta here, as well as this factor t here. This might seem minor to you, but like I said, differential privacy the constant factors matter. So the square root log 1 over delta is quite significant, and definitely this factor t is quite significant here as well, especially if you're doing a lot of iterations. So as we can see in this figure here, let me just bring up this figure. This will result in a significantly better privacy analysis than the strong composition. Recall this is just the exact same algorithm, but different privacy parameters. We can show that the exact same algorithm, the exact same parameters, will have a very different privacy guarantee, as you can see here. This is their method, the Abadi et al. Method, which is known as moments accountant. And you can see that while the strong composition guarantee would be something like, I don't know, for 360 or however many iterations you see here, we get a maybe 3 epsilon equals 3 guarantee. Here, the strong composition theorem would have given an epsilon of, say, 22, around there. So this will, I would consider this to be a decent privacy guarantee and this not to be a good privacy guarantee. So this constant factor in the analysis really makes a big difference in terms of how, accurate it is. Let me just move this up so we have some space below. But yeah, this shows, I think this really emphasizes how much of a difference there is in the privacy guarantees just by doing something different there, by doing a better analysis. And yeah, so you see, like, just using the same algorithm, it's possible to it's the same algorithm but a better analysis. So sort of in hindsight, we can say that we actually had better privacy guarantees than we thought. This has actually been done again in the sense that there's been even better analysis of this algorithm, better than the one in Abadi et al., which leads to even better privacy guarantees. And I have, if you look at the notes, you can see some references for these facts. For example, I think there's one paper by the most recent one is by Mironov, Talwar, and Zhang, where they prove a better privacy bound. In particular, they sort of improve the sort of subsampling plus advanced composition step here. That sort of combination of things in order to get something beyond this. But the question remains, like, okay, so we went from a huge jump from here to here. Now, maybe it's possible that there's another much better analysis that takes us all the way from here to here. Is that possible? Can we do much, much better? And so there is there's a complementary line of work. Say there's one work by Jagielski, Allman, and Opria, and again I cite this in the notes, which essentially asks how private is private SGD, and shows that we're pretty close to the actual privacy guarantees, in the sense that they provide attacks showing that how they essentially provide data poisoning attacks which are equivalent to privacy attacks here, showing that it's impossible for us to go all the way down to here in terms of the privacy guarantee, because there's an attack that they generate which realizes a privacy guarantee which is something more like this, meaning that the privacy that it guarantees is at most this value here, so it lies somewhere above this line. This is just an example, but essentially that's how their attacks work. So it's an interesting question to see where exactly the true privacy guarantees of DPSGD lie, but we're really not that far off from the true answer in general. So let's talk a bit about where exactly their savings come from. And to do that, we're going to look a bit more at the privacy loss random variable. So recall the privacy loss random variable. It's something like the following. We had L between y and z, where y and z are random variables. And we're looking at this random variable. Let me just write it and then we can see. I'll read it for you. This equal to t. So yeah, the distribution is the following. So you sample t according to y, and then you compute this value, and that is the privacy loss random variable with y with respect to z. So what did epsilon dp say? this said something along the lines of that, you know, the privacy loss random variable on mx with respect to m on x prime, where x and x prime are neighboring data sets, is less than or equal to epsilon with probability 1 for all, let's say, of course, for all x and x prime neighboring. So this is what epsilon differential privacy says. We've already talked about this before, but it says that the privacy loss random variable is bounded above by epsilon in magnitude. Now, what does epsilon delta dp say? Well, this is something very similar. In fact, I'll just be lazy and copy and paste this. You can copy and paste even more than that, actually. So it says essentially the same thing, but I'll write that with probability only 1 minus delta. So there's some delta probability that the random variable will be something which is greater than the value epsilon, but doesn't really tell you much. So let me just draw a picture I think I drew before, which is something like the following. So imagine we have something like this. This is, say, epsilon. This is minus epsilon. And, you know, one privacy loss random variable could have a PDF, which is something like this. And this would be pure DP. Another privacy loss random variable could be something like, I don't know, this. And as long as this shaded mass right here is at most delta, that would be epsilon delta dp. And let me just draw one more for you. We could also have some random variable, which is something like, I don't know, pretend it's the exact same thing essentially. But then we have that there's like delta mass way over here. So there's like a little bit of mass over here, the delta. And the interesting thing is that epsilon delta differential privacy doesn't let us distinguish between this blue curve and the orange curve. It just says that, you know, somewhere out there we have this amount of mass, but we don't really specify further where exactly it is. So there's some other notions which try to give a better understanding of the privacy loss random variable. And I'm going to tell you about another type of thing which tries to control not just like how much mass is here, but it tries to control the moments of this privacy loss random variable. Specifically, we're going to imagine the following quantity. So we're going to imagine the natural log of the expectation of, let's say, t drawn according to m of x of probability x is equal to t divided by probability that m on x prime is equal to t, where of course x prime is a neighboring data set, raised to the power of t. So yeah, we're essentially going to consider the expectation of, this is not a t, this is a lambda. So this is some sort of parameter here. This is sort of the interesting thing. Yeah, and we're going to say that this quantity is bounded above by some gamma. So you can see that this is kind of similar to before. Instead of just looking at the magnitude of it, you know, saying that, okay, this is kind of inconvenient because one is sort of moving the probabilities inside the log and one has it outside of the log, but really saying that this quantity inside of here is less than or equal to e to the epsilon with, say, probability 1, whereas this one simply says that it's something more like the expectation of that random variable when raised to the lambda power is less than some value. Yeah. So this kind of gives some idea of how big the privacy loss random variable could possibly be, and maybe gives a little bit of distinction between these orange and the blue curves. They're not going to be exactly the same thing as they were with epsilon delta dp. So the convenient thing is that in this case, actually, this type of guarantee is convertible into, suppose you knew a random mechanism had this type of guarantee. it's not hard to see that this implies an epsilon delta bound just by Markov inequality. So I'll just do that real quick as kind of the only / last proof in this entire lecture. So what are we trying to do? We're trying to prove that something has epsilon delta differential privacy. So what we're trying to do is we're trying to bound the probability that the privacy loss random variable is greater than epsilon. So yeah, we're trying to bound this probability. And what we can do is just write this as the following. What we're going to do is multiply both sides by lambda, and then we're going to take the exponent of both sides. Since this is a monotone transformation, it's still going to result in the same probabilities. So this can be written as probability. It's still over t sampled from the same thing. I'll just leave that out. So exp of c ln of, I guess no, I won't write it out. It's this exact same thing here. Let me, in fact, see if I can steal it. Perfect. This quantity here. The probability that this whole quantity here is greater than or equal to exp of lambda times epsilon. And from this point, what we can just do is use Markov inequality. Markov inequality, what that says is that if we take this, we can upper bound this quantity by the expectation of the this term here, this random variable, divided by this term here. So in fact, the interesting thing is just by, if you squint at it, oh, sorry, let me clarify this, not C, this should be lambda, the same lambda that we have here. So yeah, if you squint at it, this term here can be rewritten as, it can be rewritten as essentially the same thing that we have here in some sense. So like, I won't do the entire details. You can see the notes if you want it, just because there's going to be a lot of writing. But essentially, this can be upper bounded by exp of gamma divided by exp of lambda epsilon, which is equal to exp of gamma minus lambda epsilon. So this is delta, essentially. Okay, so what did we just do? We've got a lot of symbols here now, but essentially we said, assume that a distribution or a mechanism has the following bounds on its privacy loss random variable. Then that implies that if we take this lambda and we take this gamma that we have, whatever parameters these might be, and we choose some epsilon, then we can compute a corresponding delta. So all I'm really saying is that from this implies epsilon delta dp. So that's cool. It's not totally different from a differential privacy notion. In fact, it's possible to formalize this into a privacy notion. Yeah, in particular, there's a notion known as Renyi dp, which was introduced kind of in the aftermath of this paper by Mironov in 2017. And essentially, it works based on bounding moments of the odds ratio between the mechanism on neighboring data sets. So this Renyi differential privacy, or as it's often called, RDP, it enjoys all of the same types of things that we know differential privacy enjoys. For example, things like composition, being closed under post-processing, and very importantly, subsampling amplification. Subsampling amplification is really what we need in order to get concentrated differential privacy. Or sorry, it's what we need in order to get the tight, or not the tight bounds, but the much better privacy bound that we get in this lecture by this approach. So this is just a vague idea. I don't get into the details of Renyi differential privacy, but overall, this will lead to an approach which is known as the moments accountant, which I'll outline to you here. So the way is as follows. What we do is, for all lambda simultaneously, what we're going to do is compute the corresponding gamma for the following process. So what do I mean for a lambda? We're going to compute, well, sorry, let me write this out a bit and then we'll discuss it a bit. What we're going to compute it for the following process. The Poisson subsample plus Gaussian mechanism. So, okay, well, what am I saying here? I'm saying, suppose you run this Poisson subsample and then apply the Gaussian mechanism on your data set. If you do this, what type of privacy guarantees do you get? Well, we already know kind of what sort of approximate DP guarantees we get. That's sort of like the analysis that we did in the previous lecture, approximately, modulo the Poisson subsampling difference. But what we're doing here is we're going to actually compute it with respect to this this weird quantity here, also known as the Rényi, not exactly the Rényi differential privacy, but essentially trying to understand what sort of Rényi differential privacy guarantees the algorithm would enjoy for just, say, one iteration. So yeah, that tells us just one iteration and tells us what sort of privacy guarantees we have there. The next thing we do is apply composition for t iterations. And it turns out this composition is like very much, despite the fact that we're working in, no longer working in approx DP, we're now working in Rényi DP essentially. We can apply composition for t iterations, and this follows just by essentially adding up the parameters as you would expect. I won't go into details, but it's roughly it's very simple to apply composition. And then the last thing is you essentially compute what sort of, you convert this RDP into an epsilon delta DP bound, or an approx DP or ADP bound. And this is essentially done by the following, the way I just sort of described here, in the sense that I showed that if you know overall what your sort of lambda and gamma are, for any fixed lambda and gamma, you can compute it to an epsilon delta guarantee. Now the thing is, I presented this as if it was just for a single lambda and gamma, but in fact, like I said, in the first step, we really computed lambda and gamma for every single possible lambda. So what I'm going to say is, you're not just going to, we have not only one RDP guarantee here, we have sort of a family of RDP guarantees, and so we're just going to say that you use the best lambda, which corresponds in the best value of epsilon and delta. So yeah, this might seem a bit, this is all you really have to do for the privacy analysis, which we're not going to detail here, but it might sound a little bit complicated. In particular, how would you compute this lambda and gamma? How do you, for a given lambda, how would you compute this gamma? How would you possibly do this for all lambda simultaneously? How would you pick the best lambda? While I've hidden the details, I want to convince you, I want to at least tell you that it's not really it's not super challenging. In particular, in TensorFlow privacy and other modern machine learning packages for differential privacy, pretty much there's a lot of different moment accountants packages, as they're called, which let you really compute this. And the neat thing is that these are really, this is really not the way you might be picturing this as you're doing it as you go. But this is not data dependent at all. So you can in fact do all the analysis in terms of the privacy before you even look at your data set at all. So this is convenient, for example, if you think, okay, I need to satisfy epsilon delta differential privacy with some specific epsilon and delta. Well, does this set of parameters let me do that? And you'll see, okay, yes, it does, or no, it doesn't. So what you can do from there is maybe change some of your parameters, maybe add more noise, maybe reduce the number of iterations. So yeah, there's efficient software packages which allow you to compute quickly the moments accountant guarantees. So yeah, the thing is, these approaches, so we've talked a lot. I think I've detailed enough for you the approach, how it works, what the algorithm is, and a little bit about how we do the sampling and how we do the privacy loss and analysis. Now the question is it any good? And it's kind of a mixed bag here. It's okay, it's not phenomenal. Yeah, in particular, one common benchmark is the MNIST dataset. So this is a classic dataset which consists of a bunch of pictures of people who drew numbers, say like what a 0 looks like, what a 1 looks like, what they drew for 3, 5, etc. And the question is, given a picture of what someone drew as a 3, can you make a machine learning model which will correctly classify it as the number 3? So it's considered a very easy task in the non-private setting. In particular, in the non-private setting, there's approaches which get, say, 99.8% non-privately. Non-private. So this is, of course, very high. And the best we get under privacy is 98.1% with privacy, which is like pretty good still, I guess. You might think this is pretty close, and this is a result of Paperno et al. I'll leave the reference in the notes. So this is good, but it's kind of like a huge drop. In particular, if you show this to any real serious machine learning person, I think like 98% on MNIST is really not great at all. Oh, and I should tell you what type of privacy guarantee this has. This has 2.93 10 to the minus 5 dp, which is like decent differential privacy. Not incredible, but pretty decent. So that's all good. But on the other hand, there's other tasks which are more challenging. For example, there's something called CFAR 10, which is more difficult. It has like pictures of things, and you have to classify which of 10 classes they are. And this data set is known to be quite a bit more challenging in the sense you really have to do, say, non-trivial things. Nonetheless, without privacy, we can still get, say, 99.7% accuracy non-privately. But the best we know of right now, okay, there's many best things because there's different privacy guarantees you can have. But with privacy, one of the best results is 66.2%, which is, as you can see, comparatively, a huge drop in accuracy. This is not good enough. And this only guarantees 7.53 10 to the negative 5 differential privacy. So it's not a good accuracy guarantee, and it's not a good privacy guarantee either. So I would say that right now we can't really we can do MNIST pretty well, not incredibly, but we really can't do CFAR 10. There's a lot that still needs to be done in order to improve the state of the art in private machine learning. All right, let me just comment a few more remaining things before we move on to the next thing, the private aggregation of teacher ensembles. So there's a few remaining comments, and what I want to really highlight in the rest of the segment is a few differences between the private setting and the non-private setting. For example, the way it's kind of designed is that DPSGD can be a drop-in replacement for SGD. But in fact, there's quite a few qualitative differences in terms of how things behave. So you can't just, there's really a lot more to be done under differential privacy. You can't just think it's solved because we have this algorithm. There's a lot of new phenomenon that we have to understand. One difference, for example, is the speed of DPSGD. So let's scroll back up to the algorithm and recall that DPSGD is, what does it do? It's pretty similar to SGD, but the main difference is the fact that we have to clip each point and then we average them and add noise. So this might seem pretty much the same thing as the non-private setting, where you just you don't clip them, and then what you would do in the non-private setting, let me just state it so that we're all on the same page. You would compute the gradients for all the points in a mini batch. We would then average them and take a step in the negative direction. The difference here is that we have to clip each individual points to an L2 ball of radius C and then average them. So it turns out that this clipping procedure, you might think it's kind of obvious, okay, you just do this, but this is not something which is, it doesn't really play nice with modern machine learning frameworks. Why is that? Because typically what happens is a lot is done under the hood when you sample a mini batch and try to average the gradients. In particular, things like TensorFlow or PyTorch will send them off to the GPU and process all of them in parallel. It'll process all of them in parallel, which is where a lot of the speed up in modern machine learning settings is obtained by just doing doing SGD in parallel using things like GPUs and tensor processing units nowadays. But this clipping procedure kind of throws a wrench into the whole works by adding something that wasn't really there before. And in particular, things aren't optimized to be able to handle this clipping procedure. So the sort of takeaway, what I'm trying to tell you here is that clipping is slow. Now, there's some ways of getting around this. What are some ways of getting around this? Well, one way is changing the algorithm slightly. Instead of, what it does is, what we would ideally do is clipping and then averaging the points. Instead, what one can do is average and then clip. The drawback is that you would have to add, a significantly larger amount of noise in order to give the same privacy guarantee, so that doesn't work naively. But what you can do is kind of have some sort of trade-off here with a strategy known as micro-batching, where say you just take maybe 4 or 8 samples at a time, 4 or 8 data points. What you do is average them, then you clip them, and then you average all of these clipped micro-batches. The result is that you're going to get something which is faster, but this will come at the cost of adding more noise, and you'll get a weaker privacy guarantee. So this is not the ideal situation. It's faster, but it lowers your accuracy. So if you really care about accuracy, that's not the approach you want to necessarily do. In particular, you already lose a lot due to privacy. Micro-batching will lose even more accuracy as well. So that's not a good, that's not the best solution. There's other approaches which, kind of try to exploit the auto differentiation libraries as best we can. And by setting up problems in the right way, there's, for example, a trick by Ian Goodfellow, which is exploited in the original Abadi et al. Paper. And this is decent, but still leads to fairly sizable overheads, even if done carefully. So in particular, it seems that, the approaches are rather different here. And you have to really note that there might be big slowdowns when you do differentially private SGD. Here's a figure from a paper by Subramani, Vadivelu, and myself, which shows some of the extreme cases here. So you can see in the top half of this, you can see at the bottom half of this, sort of the non-private cost of running a differentially, or running SGD versus or DPSGD in the top half. On a particular LSTM network. This is a more complicated neural network architecture than what we described at the beginning of this class. But you can see that the runtimes per epoch are fairly fast without differential privacy. For example, in PyTorch, if you do a batch size of 256, it'll take just 2.56 or 2.4 seconds per epoch. However, if you add in differential privacy and you try to do DPSGD naively, then some approaches won't even work because they don't support these types of networks. For example, Goodfellow's trick, which I mentioned, that was only for simpler networks, so they don't even apply to this sort of thing. Certain approaches don't even work. But other approaches will, which do work. This is essentially a sequential processing of the points, and you can see that this takes 200 times as long, roughly. Interestingly, it seems like choosing the right tools for the job sometimes leads to big running time improvements. For example, JAX, which is a relatively recent machine learning framework, it seems like it has the right tools to make it be able to handle differential private machine learning much faster. In particular, you can see that there's just a maybe less than 3 times about 3 times speed hit when it comes to running it with JAX. Running it in JAX with differential privacy versus not. Which might seem like a lot to you, but compared to these other times where it's like maybe hundreds of times worse, And it seems like JAX is one of the faster methods. I won't get into it much more here, but I'll just say that it's kind of due to things including a vectorized mapping operation that JAX supports as a low-level primitive, as well as some of the compilation, just-in-time compilation features that it also supports. So yeah, this is just one thing showing that the speed of DPSGD is something that you have to be concerned with now in the private setting. There's other things including, say, changes in architecture. Like, I'll just touch on two things here real quick. So one thing is the fact that you might want to have different activation functions. So for example, the activation function ReLU seemed to be the most effective activation function in the non-private setting. It's kind of a massively adopted, everywhere you might look. Non-private, yeah, ReLU is king. But whereas a recent result of Paperno et al., which again I cite in the notes, which you can check it out, it turns out that actually previous methods which were thought to not really be the right thing, such as Tanch, are better. So it seems that you can't just port things directly from the non-private to the private setting and hope for them to work out the best. Sometimes you have to do new things, and they give some sort of empirical examination as to why Tanch is better than ReLU in this setting, or generally sigmoidal shaped activation functions. Another difference is size versus noise. What do I mean by this? So typically in modern machine learning settings, a bigger neural network is better. For example, there's things like, GPT-3 is one of the hottest new things, which is a neural network model with hundreds of billions of parameters. Generally, over-parameterized neural networks are the way to go with as many parameters as you can possibly train on. This, however, is not a good rule of thumb in the differentially private setting. Why is that? The reason is because remember when we were doing DPSGD, we compute the gradient, and the dimensionality of the gradient is going to be proportional to the number of parameters. And we have to add noise, essentially, which is going to depend on the square root of the dimensionality of the gradient. In other words, there's going to be a square root in the number of parameter cost that we have to pay when we're doing differential privacy here. So there's a kind of a trade-off. A larger network will give you more capacity or more expressivity, as the term that they like to use, but it will also require you to add more noise at the same time. So you have to kind of balance these two. Choose something which is big enough to represent your function maybe, but not big enough to necessitate huge amounts of noise. So yeah, even more care might need to be taken when you're choosing your architecture with differentially private machine learning. And the last thing I want to touch on, which will kind of even segue into the next and final component of the lecture, is exploiting public data, in the sense that classically we picture that our training data is just fully private. But it turns out that sometimes with just a little bit of public data, we can do something much better than what we could do without. For example, let me mention a common challenge in differentially private machine learning is hyperparameter tuning. What are hyperparameter tuning is a big challenge in non-private machine learning even. The common way is just to basically do a grid search over parameters, choose just iterate over all possible hyperparameters and see which one gives you the highest accuracy on some sort of validation set. They're typically time consuming, but it's something you can do maybe in parallel, maybe using some something like Bayesian optimization rather. Bayesian optimization gives you often a faster way of searching through these hyperparameters. But the point is, in the non-private setting, it's kind of annoying, but something you can do given enough time. The thing is, if you try to do this naively in the private setting, what you would do is be running multiple analyses on the same private data set, which would eat up your privacy budget with each time you did it. This is, of course, a huge problem, and there's even more hyperparameter that you have to tune here than before. For example, now we have things like the clipping norm, which wasn't there before. The number of epochs. Before, maybe you would just like run it as many epochs as you need, but here you might have to cut it off. Yeah, the point is, I spelled hyper wrong. The point is that hyperparameter tuning is a much bigger challenge in the non-private setting, just because of the fact that we also have to deal with a privacy budget. So what a lot of people do in practice, which I'm a little bit troubled by, I think this is like, you know, if you're honest about it, if people think about it, then this is okay. But in the private setting, people nonetheless still just essentially do hyperparameter tuning, but do not account for that in their privacy analysis. Like say, okay, we came up with these parameters somehow, not mentioning that these were done via hyperparameter tuning on the private data set, and then output what the algorithm gives on that data set, sort of assuming that they were magically given these hyperparameters by God or something. I don't know. So if you want to do something more honest, there's a few different options. One is results by Liu and Talwar, which was from 2019, which gives a kind of method. It's kind of like a generalization of the exponential mechanism, which allows you to essentially pick the best hyperparameter the best hyperparameters in hindsight. You kind of can run them all and see which one's the best, and this costs you like some small factor in your privacy, maybe like a factor of 3, maybe a factor of 2 if you do it best. So there are some ways of dealing with this, but this one, for example, is a little bit more theoretical in nature right now. But you know, another thing that you can do is, like the title of this little segment suggests, is exploit public data. So what you can do is, you know, just use you can also do it on public data. What I mean by this is that imagine you have a public data set which is somehow similar to your private data set. This could be, for example, a set of users who have opted in and say, okay, I don't really care too much about privacy of my data. You can do whatever you want on it. So in particular, you're free to do hyperparameter tuning on this subset of the public data at no privacy cost. That's okay. Another thing you could do is you could potentially even use public data, which is somewhat similar to your private data, and you know, do most of the training on this public data, and then just do some fine tuning on the private data set. I still spelled hyper. Okay, but the point I'm trying to get at here is, imagine you have some big neural network, you know, all these layers, blah, blah, blah. Something like this. One thing that some people do is, first, step 1, train on a public data set. So say some public data set, maybe you could just like scrape, if you want to do a language model, maybe you can scrape Twitter or Reddit or anywhere where there's a lot of text, and just like train a model on that. And then the second thing you do is freeze most layers. Like say maybe all of these ones, you say don't change the parameter vectors at all there. And then privately train the remaining. So this has the benefit of, you know, getting you to a good starting point using a public data set, which comes at no privacy cost, and then freezing most of the layers will result in just having a smaller number of parameters to train on. Remember I said you pay something which is proportional to the square root of the number of parameters. Well, if you freeze everything but the last layer, then you don't really have to add all that much noise. So yeah, in fact, this is done in the original Abadi et al. Paper, where they kind of train on a public data set, say CFAR 100, which is related to CFAR 10. But then they do their private training on CFAR 10 to see what type of accuracy they can get with this sort of fine tuning. So that's it. There's a lot of stuff I mentioned today in terms of like DPSGD and making this as good as possible, and some of the nuances which come up in the differentially private setting. For the last portion of this lecture, we'll talk about how to do private aggregation of teacher ensembles, which is another approach which also uses public data, but in a very specific way. Yeah, so be sure to join us for that.